Welcome to the 32nd International Conference on Formal Power Series and Algebraic Combinatorics. My name is Jang-Soo Kim. Today, we will have 3 speakers. Each talk is 25 minutes long with 5 minutes in between for questions and a short break. There will be a coffee break at the end of the session if you have time to stick around. Everyone is welcome to participate. The chat monitor for today is Eric Marbeck. Let me introduce our first speaker, Shubham Sinha from UC San Diego. He's going to talk about random t-cores and hook length in random partitions.
Today I'm going to talk about my research work on t-cores of a partitions and hook lengths in asymptotic limits. So we'll see what it means soon. This is a joint work with Professor Arvind Iyer from IISc. So there will be 2 parts in the talk. The first part we will describe what we found about the distribution of the size of t-cores of size lambda. In particular, we'll show that the distribution converges to a gamma distribution when things are defined in a way that it makes sense. And secondly, we say that the core of lambda for a random partition, uniformly random partition, is of order of square root n. The second part will be mostly about congruence classes of hook lengths, modulo t, in a random cell partition. Here we developed some new technique, which we call it smoothing. And using this technique, we will prove that the probability that a hook length is congruent to I mod t. So this approaches 1 over t as the size of the partition grows large enough. All the references can be found in the paper, which is on arXiv. Let's start with some preliminaries. So we'll have our main object is partitions. We denote Pn to be set of to be number of partitions of size n, and capital Pn to be set of partitions of size n. Here we have displayed the 5 partitions of size 4, and this will be always be using English notation for Young diagrams. Given a cell C in the Young diagram, so let's look at the example. The hook corresponding to cell C is precisely all the cells which is on the right or to the bottom, including itself. And a rim hook is the boundary joining the 2 ends of the hook. So in this case, this blue shaded region is the rim hook. And the hook length of is the size of the hook or the rim hook, whichever one you prefer, both are same. The t-core of a partition is obtained by removing as many rim hooks as possible. So in this case, we have shown a sequence of steps where each step we remove a rim hook of size 3 to obtain a partition in which there is no rim hook. If we write down the size of rim hooks corresponding to cells, you see that there is no 3 hook here. It's well known fact that this it does not depend on the order in which we remove the rim hooks. So that we can see later on in my talk as well. Now some more definitions. A partition lambda itself is called a t-core if its core is itself. So that means that there is no rim hook of size t in that partition. And the partition is called t-divisible if the size of, like, when you take the core of the partition, you get an empty partition. Here we denote frac ct and dtn to be the set of t-cores and t-divisible partitions respectively. And the small ct and the small dtn will corresponds to the number of t-cores or t-divisible partitions of size n. Here is an example. The first example is of a partition of size 9, which is a 3-core partition. As you can see that there is no rim hook of size 3. And the right hand side is a 3 divisible partition. Here I have shown you the sequence in which you can remove to obtain an empty partition. So the 3 core of this partition is precisely empty. So let P, dt and Ct be set of all partitions, all T divisible partition and all T core partition. So it's basically union over all n. Then we have this theorem which is very useful for us, which is called partition division. It is the projection between set of partitions and set of to the set of T core partition times set of T divisible partitions. So what is this projection? So as you would expect, the first part of the projection for any given lambda, this T core partition is precisely the core of lambda. And then there is a second part, nu, which is the T quotient, which I will not define until the second part of my talk. But let's assume that that we know that this exists for the rest of the first part. It satisfies an important property that that the sizes add up. Basically, size of lambda should be size of the core plus size of the quotient, whatever that means. This is a small generalization of Euclidean division, which can be written in this term to be the projection between a set of natural numbers to set of remainders, which will be corresponding to the T core, and set of T divisible numbers. We know a few facts about these objects. First of all, there's a famous Hardy-Ramanujan formula for asymptotics of number of partitions of size n, which is given to be this beautiful expression. And then we have similar analysis. Using similar analysis, it's known that the number of T divisible partition have a similar asymptotic expression. But the third object, the number of T cores, is rather difficult to get your hands on. One fact is that there is no such asymptotic result, first of all, because it's more complicated and it's not exponential. One thing I want to tell you is that if you take T equals 2, the number of T cores, the only T cores are the staircase partition, in which case C2n will be 1 only if n is triangular number and 0 otherwise. But there is another characterization, at least for the number of partition. It's the number of tuple, p0 up to pt minus 1 is a t tuple of integers which satisfy two expressions. One is their sum should be 0, and second is some quadratic equation on these t variables which defines an ellipsoid. So I've purposely not put what the equation is because that won't be relevant for us. It is relevant to prove all the things which we are going to do, but for the talk we can skip it. Okay, so and we'll see what these PIs mean in the second part of the talk. So let me describe you the first lemma or theorem of our paper. So instead of talking about the T-core partition, number of T-core partitions, we take a slightly different object which can be easily described as n grows large enough, like the asymptotics are well behaved. So what do I mean? So first of all, let's define the CTN. It's the number of T-core partitions which appear as a core of lambda, where lambda is a partition of size n. A remark that when T is a prime number, this number is something natural appearing in the T-module representation theory of permutation group. It's basically number of T blocks. We won't go into the details of this, but because we will do mostly the combinatorial analysis in this talk. A simple combinatorics can tell you that this number is certain sum of the number of t-cores. So once we have this as a sum of number of t-cores, you see that I told you that it's, so if you want to find this number of t-cores of any size, that's basically trying to find certain lattice point on the ellipsoid. But when you sum it up, so in some sense, like you have the certain sum can be approximated by the volume of such ellipsoid as n grows large enough. And that's precisely what helps us to find an asymptotic for this quantity, which is given to be order of n per t minus 1 over 2, and I will describe the constant for now. But this result is super useful for what's about to come, which will be the main theorem for us. It's about the distribution of size of t-core of uniformly random partition lambda of size n as n grows to infinity. Okay. So let's set up the stage where this distribution makes sense. So given any random partition lambda, our random variable is described on the set of natural numbers, which basically takes the value of the size of the core of lambda for any random lambda. The probability mass function of yn, this random variable, can be shown that it's the number of partitions whose core is of size k over number of partitions in total of size n. And using partition division, which we described earlier, it can be written in terms of this number of t cores and number of t-divisible partition of certain sizes over n. We are interested in the convergence of this distribution of the size of the t core of lambda. To do that, we need to do certain kind of scaling if you want to make some asymptotic sense. For example, it's same as looking at binomial distribution and asking that the convergence of binomial distribution, and it's a famous result that it's converges to some normal distribution. But to make sense, you need to scale your distribution correctly to actually to have handle on both on this binomial distribution. So that's what we do. We take xn to be continuous random variable, which is scaled by square root n, and to make it defined on the whole of positive real line, we have to take the step functions whenever it's not integer over its square root. So it turns out that this object is correct quantity to express when you scale it down, and after scaling you get a random variable with probability mass function this, and you can see that the integral is 1, so it's the correct thing to look at, and this identity is directly coming from partition division. Okay, so what do we prove? Our main theorem of our paper is to show that this random variable xn converges weakly to a gamma distribution random variable x with shape alpha equals t minus 1 over 2 and rate parameter beta to be pi over root 6. So just remind you what gamma distribution is. It's the distribution with probability mass function is given by certain power of x times the exponential of minus beta x. So it's a generalization of the exponential exponential distribution. So well, we get that this is we get a nice distribution convergence, and here is the figure where to the left we have cumulative distribution function, and we see that as t equals 5 and n goes from 20 and 62 and 103, the dotted lines seems to converge to the expected to the distribution written number in asymptotics. While on the right hand side is the probability mass function, which will not converge. So that's where the weak distribution is coming from. So all the convergence happens in weak distribution in cumulative in the CDF. Okay, so but that's good enough to show that the expectation of the size of T core is of order of square root n. In particular, it's t minus 1 square root 6n over 2 pi. And so the figure 2 here precisely show you two things. One is the function square root 6x over pi, and which is the corresponding asymptotic expression. And the dotted lines are the exact exact expectation of the size of 3 core. So we have the main results here. Now a simple nice corollary, which leads us to the second part of the talk, is that when you take a uniformly random partition C in a uniformly random partition lambda, the probability that the hook length of C is divisible by T is exactly 1 over T. It's 1 over T when n goes large enough. So it converges to 1 over T. So how do we prove that? Like this fact is based on a simple observation that the number of hooks which are divisible by T decreases by exactly 1 when you remove a T-rem hook. So for any partition lambda, the number of cells whose hook length is divisible by T is exactly n minus the size of T core of lambda over T. And as this quantity in expectation grows as square root n, then when you take the probability, when you divide by n, you get it converges to 1 over T. But the same argument does not hold for a general mod congruence classes mod T for the hook length. So here's an example where we take lambda to be 6431, and I've written down all the hook lengths of the cells. And in this table, we noted down what happens to hook lengths modulo 4. So for 0 mod 4, you see, so this is before removing the 4 hook, and this is after removing the 4 rim hook. So you see that, as I said earlier, the number of rim hooks hook lengths whose size is 0 mod 4 decreases exactly by 1, which is good. But that may not be the case in other situations. For example, for 1 mod 4, it drops down from 5 to 3. So it drops down by 2, while for 3 mod 4, it doesn't drop down at all. To go over this problem, we have to develop some new theory. And to do that, before that, we want to introduce the notion of abacus, which is used in most of the paper, like even the results which I mentioned above. We use this notion to prove most of the things. An abacus is an infinite word in some sense, that is basically a sequence, is a function from z to 0, 1. So it's like 0, 1 word which stretches in both directions, in right as well as to the left, with the constraint that when you go far to the right, it's all zeros, and when you go far to the left, it's all ones. And an abacus is said to be justified if there is a position. So in this case, this is a position to the left of which it's all 1, and to the right, and it's the position, it's all 0. And we call the proposition of justification to be the place where that thing occurs for a justified abacus. An abacus is called balanced if when you push all the ones to the left, so like you push everything to the 1 to the left, and then you see the positional justification. The positional justification is exactly as 0. So here, I'm not mentioning all the positions. I'm going to use this underline notation to talk about position 1, 0, so position 0, and then next will be position 1, 2, 3, and so on, -1. Okay, so why is it important? The importance comes from the fact that there is a natural bijection between the set of partitions and set of balanced abaci. So to see what the bijection is, this bijection is given by simply walking along the partition and noting down the steps as the up step as 1 and the right step as 0. So as you see, like when you're walking all the way from the south, it's all ones infinitely many times, and then you hit the partition and you get 0, 1, 0, 0, 0, and so on, and you end up going east, which is all zeros. So what more? A cell C is in bijection with, so can be described by the 0 step, which is taken to the bottom of the hook, and 1, which is taken at the right end of the hook. So it's basically a cell corresponds to a 0, 1 pair, which is what I described here. Moreover, so what is the hook length of the cell? So in Abacus description, the hook length has particularly nice form in the sense that the hook length is precisely the number of position which occurs between the 0 and 1. So it's the difference in position, which is in this case 4. As you can see, the size of rim hook is also 4. And when you swap this 0 and 1, is precisely the step in which is the process of removing the T rim hook. So you can show that the things in the middle or to this to the both sides does not change when you remove the T hook. The only thing which changes is swaps. It's basically pushing 1 from this position to 4th step to its left. Okay, so since we are going to talk about T cores, where so that's same as in that case when you're removing the ones exactly to two T steps to the left. So the only thing which we care about is in terms of position. So if you look at an abacus, so in terms of position, you have to only look at the ones which are T steps away from each other. So in particular, you can look at positions mod T and look at those subsequence sequences which describes you the 0 mod 3 positions gives you another 1 abacus, 1 mod 3 position gives you another, and 2 mod 3 position gives you the third abacus. So in general, you have T runners. So these are called runners, and which are given by the positions mod T. Now in this scenario, what is the T core? So as I mentioned, removing a T rim hook is just swapping 0 and 1, which are T aparts. In this description, it's basically pushing the ones to the left. So when you push all the ones to the left, the final abacus, what you get by reading it off, like putting back together in one runner and then read off the core, you get the core is precisely the one which we saw earlier, 211. Moreover, so what's more interesting about this is that for the T cores, forget about the internal structure of these T runners. So it only remembers where is the position of justification for each row, and this position of justification can be noted as these PIs, which I described earlier while describing them by another describing core. So these PIs are has contains all the information to describe the core, where the sum of these PI should be 0. So now the cores are basically position of justification. So they describe positions uh, when after pushing all the ones. So the quotient, so if you want a bijection between lambda and this core and quotient, this quotient should technically have the everything which is the internal structure of these lambda i's, which are the t runners of the partition. So that's what happens. The t quotient is defined to be so how do we define that? We basically take the t runner of the partition, and then you shift each row to make it balanced. So when you shift each row to make it balanced, you forget how much shift each row has. So you forget the position of justification, and then you read off this partition, and you can show that the final partition, when you read it off, it's actually a t-divisible partition. For the reason, since all of the rows are justified, when you push all the ones, you get the empty partition. And it satisfies all the properties of partition division. So now let's come to the main result of the second main result, which is if you take a random cell in a uniformly random partition lambda, the probability that the hook length of this cell is congruent to I mod t is precisely is asymptotic to 1 over t as n grows large enough. Okay, so to do that, so these are some certain times where I feel that the proof might be more enlightening and more interesting than the theorem itself. And I hope that these techniques can be used in other places. So let's start. So if we define an action of the permutation group on the t-divisible partitions, and how do we do that? We basically permute the t runners. So there are t rows which is permuted from given by the permutation sigma of st. So we have a nice description of this action. And we can extend this action of permutation group to set of partitions by using partition division, where we keep the cores constant. Basically, you have a trivial action on core and the above given action on the t quotients, which are the t divisible partitions. Now, a B smoothing of a partition, which we denote by C nu B, is union of cells in the Young diagram whose corresponding 0, 1 pair are at least B plus 1 columns apart. So, so let's see this example. Nu equals 7, 3, 2. I have written down. So this is a 3 divisible partition. So each one of the rows are balanced. Now you look at say this one, and you're looking for a C nu 1. So this should correspond to all the cells which are at least 2 distance apart, column wise. So in this case, this one, the corresponding cells will be precisely these 4 zeros. So you get 4, and for the next one, there is no zeros. So you can see that the subpartition, what you get is 4 of 732. So a general remark is that the C nu B is always a subpartition of nu, of the t-divisible partition, and it gives you a sequence of subpartitions. Moreover, this B smoothings are invariant under the action of permutation group, because so this is something which you just have to take note down. So this is important for us. And why is it important? It's important because it jumbles up all the congruence classes of cells. So what do I mean by that? So given a cell, say 1 and 0, the corresponding congruence class depends on the relative position of the rows. So in this case, it will be 1, the congruence class. And when you permute it, and when you remember these cells, 1s and 0, and see where these cells go in the permuted uh, uh, in the after permutation, you see that this 0 1 cells takes in all possible congruence classes which are not 0. So basically, whenever I is not 0, the cell being the probability of cells in this B smoothings being congruent to I mod t is precisely is will be independent of phi because of this jumping up. So what do we do? So we have B smoothing defined for t-quotient partitions, but for any given lambda, we have this row which is the t-core of partition, and given this t-core partition gives us certain information which helps us choose this B. So in the C new B, we choose this B lambda in terms of the core, which is here we define it to be max the distance between max between of the difference between these PIs, which describe the core of the partition, and we call it canonical smoothing. And this B smoothings are defined for T quotient, so these are obviously subpartitions of the T quotient. Okay, so this is the main lemma, which basically tells us that this canonical smoothing can be thought, the cells in canonical smoothings injects to the cells in partitions, and this injection is not, so it cannot be considered as a subpartition of lambda, but it's anyway injection, but it has this nice property that the hook length modulo t remains unchanged. So the congruence class does not change. So what happens is that in lambda you have this image which jumbles up all the congruence classes. So it's uniformly distributed for the non-zero congruence class of Oaklands for this image. The proof, so to prove our main theorem, we just have to show that this phi c lambda, this image, consists of majority of cells of lambda, and that's our next lemma, which tells us that it's that the difference between lambda and this image of the canonical smoothing is order of n power 3 or 4, which is less than order of n. Hence, in asymptotic, this won't matter, and this jumbles up everything. So like in the first part, we had already shown that for cells with hook length divisible by t is the probability is asymptotic to 1 over t, and in the second part of the talk, we showed that cells in this image is independent of I. The probability of this hook length being I mod t is independent of I. So using these two things, we prove our main result. Okay, so let me summarize what we have done. So there are four main things which we have done in our paper. One is we showed the main result, which I didn't go over the proof of that we showed there's a convergence in like weak convergence of probability of the size of the distribution of which is the size of t cores of random partition to gamma distribution, which gives us a second result where we say that the size of t core of a partition lambda is of order of square root n. Then there's the third one, which is we construct this new object called smoothing of a partition, which I feel can be further explored. And the fourth part is we showed that the hook lengths of randomly distributed modulo class of T. Okay, thank you everyone.